Hey everyone, welcome to class. So in this lecture, we're going to be looking at chi-squared tests in R. So you will have already at this point looked at the theoretical backing for chi-squared and how you would maybe start to look at that by hand, right? Comparing expected and observed values to see if there's a non-random difference between these categorical groups. But now we're going to take that a step further and show you how to work on that in R. So again, with inferential statistics, when we only have categorical variables, these are variables like nominal and ordinal. And if we have two categorical variables of either kind, we're going to use chi-square tests. We also could use a one sample chi-square test we know when we have one categorical variable that we care about. And if we have two, we can use the bivariate, which we've kind of nodded to so far. Again, it's going to test our expectations of categorical and nominal variables, seeing if they're equally prevalent or if there's a non-random difference in the frequencies in these numbers of groups. So we're going to be looking at a lot of tables and showing you how that's the foundation of the chi-square test in R as well as by hand. So again, remember it's non-directional tests only. It's similar to t-tests and ANOVA because we're calculating a test statistic, comparing it against critical value and getting a p-value out of it. So those three different things are going to be important, right? They're going to get the our chi-squared statistic out of our R output. We're going to compare that to the critical value looking at a table, right? But we know we can shorthand this by looking at the significance value or pick a p or the p-value just to kind of make a quick judgment of whether or not we think there's a significant or non-random difference. But we're going to get the same sort of things from this sort of inferential statistics test as we would in other cases. So you will have already seen this already. Remember that the chi-squared formula is going to be looking at the differences between observed and expected values to see if like a frequency in that that table is random or not. So we're going to use the paper data with a hypothesis that there's going to be a non-random difference in the rates of Democrats and Republicans and independents. So there's going to be significantly different numbers of each of those groups in our data. So there's going to be meaningful differences in the numbers of each partisan groups. Since there's only one categorical variable in this case, we're just going to use chi-square, a one sample chi-square. So the setup, the foundation of this code is still based on tables. So we're going to start by looking at some tables. We're going to first make them using the table function, and we're going to select out the variable that we care about. So we're going to start with the table function. And in that table function, we're going to select out from the paper data _3, right? This is the third version. We wanted to have a certain version for the last kind of part of the homework. So from paper data 3, the $ selects out the variable that we want. And in this case, Dem party ID is that variable that we care about that has all three of the different party identification labels. So in this case, there are 1,167 Democrats, 934 independents, and 977 Republicans. Do all of these values occur at the same rate, or are there meaningful differences? Are there meaningful differences between the amount of independents versus Republicans and so on and so forth? Is this number right here, this 1,167 Democrats, meaningfully different, i.e., would we expect to have that many more Democrats than everybody else? Does that make sense based on the way we did our kind of data collection? So those are the kinds of sorts of questions we can get at with this one sample chi-squared. And remember, if you look at the code book for this particular example, we see that the 1, 2, and 3 are the labels that are assigned to Democrats, independents, and Republicans. So 1, 2, and 3 denote the label for that party. Our code and our test is going to be the chi-square test. CHISQ.test. So chi-squared, chi, the Greek letter is this kind of fancy looking X with a raised and exponentiated 2, chi-squared. And we're going to run that by adding the table into this function. So we're going to start by naming the X variable that we're going to use. And then having that equal to our table function that we want. So we're going to embed the table function that we had here into our chi-squared test where X is equal to that table. And so we then get some output where our chi-squared statistic is 29.967. Our degrees of freedom are 2, and our p-value is 3.11 e to the -7, which means it's 0.000000000311. So it's a really, really small number, definitely less than 0.05. So we'll talk about that interpretation in a second. But remember, the chi-square is always positive, and as it increases, our values are more extreme, or we can have more certainty that they actually are non-random differences between these different cells. Our degrees of freedom are 2, and we'll see that that critical value is going to be 5.99 based on the following table I'll show you. So if we did this by hand, we knew our degrees of freedom, or D, on this far left-hand column was 2. And then we knew our significance level that we like to use is 0.05. We'd go down to 2 and over to 5. And we'd see that 5.99 is that value that we care about. And so that's going to be what we're going to compare. 5.99 is what we're going to compare this 29.967 to. So once we have that, remember, we go back and start to think about a normal curve. And we know that in the case of this data, so 5.99 is our critical value. It puts us way outside that 3 in a tail. And we know that 29 is much bigger than 5.99. And because it's more extreme, we can reject the null hypothesis that there's no meaningful difference of group. And there is a meaningful difference in favor of our working hypothesis. And this will again correspond to a p-value of 0.05. So we can reject the null. So a recap here, from our code, we can deduce that there's a meaningful difference between the rates in which all of these partisans are in the data, and it's not at random. We get a chi-squared statistic or an x-squared statistic in the output of 29.967. This is much greater than our critical value of 5.99, with degrees of freedom of 2 and a p-value that's very, very small, close to 0. And again, that's your code for it. So this is when you only have one categorical variable, but in many cases you'll want to have you'll have 2, and you'll want to know if there's meaningful differences at the intersections of those particular variables. So let's move into a bivariate example and how that works. It's still based on this idea of comparing the frequencies against the expected in each of these different variables and seeing whether there's a meaningful difference between the different rates. So in this case, we might hypothesize that there's a non-random difference between marital status in each of the political parties in the US, i.e. maybe there are more married people in the Democratic Party or more married people in the Republican Party. You could see a world where a causal mechanism would be because Republicans are more interested in moral traditionalism and maintaining family values, that there are going to be more married people in that party. And so we're still going to be doing this sort of table comparison. Now, remember that each of these numbers, the 1, 2, 3, and the 1, 2, 3, 4 on the outer bars, right, on the across the top and on the bottom, denote labels for those variables. And so our rows are the different Dem party IDs, and the columns are the different Dem party IDs, right? So Democrat, Independent, Republican, those are our columns, and our rows are the different Dem maritals. So that our X is first, in this case, our Y is first in this case, and our X is second. And in this particular case, we want to understand whether there's a meaningful difference between the rates at these intersections. So say, I need to go back and look at what 1, 1 is. But in this case, is there a meaningful difference between Democrats who are at level 1 of marital status versus independents at level 1 of marital status, right? So 547 versus 417. That's kind of what we're starting to think about here. I'm now going to show you. So this right here is not the best way to show that table. This table here, this table function is the base R version of creating tables, but there are a lot of additional packages like SJPlot that I'm going to show you in this particular lecture that create much better frequency tables. That's what we're looking at, is frequency tables or crosstabs. Those are language that we'll kind of start to use moving forward. So there's just better packages that we can use to do this. So I'm going to show you one from SJPlot. That's the name of the package. And the function in SJPlot we're going to be using is sjt.xtab. So this is a cross tab from the SJPlot package. And we see that in one case, we've got our Dem party ID. Generally, do you think of yourself as a Republican, Democrat, or Independent? Cross-tabulated by Dem marital. Are you now married, widowed, divorced, separated, or never? So the reason why I love this is it gives you all of the labels to start. It's going to take the labels from that SPSS file and it's going to put them on the tops of the columns. So we know that 1 is married, 2 is widowed, 3 is divorced, 4 is separated, and 5 is never married, as opposed to this, where you'd have to go back and look at the code book manually. This creates it for you. And again, we know that there's 1 is Democrat, 2 is Independent, and 3 is Republican. And we can look at the amount of people. So there are 547 Democrats who are married. There are 417 Independents that are married, and there are 604 Republicans that are married. So maybe our causal mechanism and our hypothesis of there being a meaningful differences between parties and marital status, with maybe more Republicans being married, might have some weight to it. And so we're going to start to look at the fact that we can use this function to not only get the crosstab, but also allow us to get at the chi-squared statistic, the bivariate chi-squared statistic from here. So we see that the x squared at this very bottom right-hand corner is 115.041. And we're able to see that that has a degrees of freedom of 8 and a p-value of 0. So we can tell that there's a non-random difference between the frequencies of people in different marital statuses by partisanship, which is substantively interesting, right? Substantively interesting just means that there's like an interesting political phenomena happening here, right? So I want you guys, when I give you guys the code, the supplemental code that goes along with this video, I want you guys to think about for your final paper using sjt.xtab, and I'll start to kind of show you guys what this code looks like in terms of being able to produce outputs that you can then kind of screenshot and put directly into your paper versus something like this, which it's cut off a little bit because of the PowerPoint slides, but it's just not as pretty, right? And so it's got all this extra additional like dollar signs here on the left. It's not as readable. It's got a lot of like R jargon in there versus this looks beautiful, right? So we see that the chi-squared of 115.041 is the same. We also see that the p-value is the same, so they rounded down to 0. So 2.2 e to the negative 16 is so tiny and infinitesimally close to 0, they rounded down. So this is a perfectly fine thing to put in your final paper. And I'll show you what the equivalent versions of this look like for some of our other tables. But I wanted to start introducing this now that you have some understanding of what these inferential statistics functions look like. I want you guys to start thinking about how we can make them prettier in order to put them in our final papers. So again, your chi-squared tests are for these categorical variable comparisons. You can just compare the frequency of variables in one particular variable, the frequency of the different categories in one variable, or you can look at it across two. And moving forward, we're going to go into correlation, and then we're going to end on regression and a little bit of visualization tools for your final paper. But generally, this will give you a good place to kind of start thinking about the sorts of things you can test in your work.